The topic of today's video will be Cauchy integral formula, and we'll see that these Cauchy integral formula are just direct consequences of Cauchy's theorem, as we discussed in the last video, right? So basically we have two versions of this Cauchy integral formula. I will discuss them one by one, right? Okay. Let f be an analytic function within simply connected domain D, right? And capital C is a simple closed contour, or you can write it as curve, lying inside D, right? Then for any point small a inside C, the value of this integral is equal to 2 pi eta times f of a, right? So this is a statement of Cauchy's first formula, right? This is Cauchy's first formula. You need an analytic function small f, right, in a simply connected domain D, right? And inside that there is a curve C, which is a closed curve, right? Okay. Then for any point inside that curve C, this formula holds, means the integral of fz over z minus z dz equal to 2 pi eta multiplied by fa, right? And rather we should write this 2 pi eta here, 1 over 2 pi eta. Fine. I will draw the picture first. So you first have the domain D, right? This is the domain, right? And you will see that domain is always an open connected set, right? It is a boundaryless set. This is a domain D, right? And inside this domain D, you have this simple closed curve, right? C. Fine. And if you are saying that f is an analytic function over this red region, domain D, then it is a direct consequence that f is also analytic inside C and as well as on this curve C, right? Because f is analytic over this red region, right? And this is your point A. A is any point on it. You can take this point anywhere, but inside of this closed curve C, right? Then the formula says that the value of the function, analytic function at the point z equal to A, which lies inside this closed curve C, is actually given by the constant 1 upon 2 pi eta multiplied the value of the function, right, over the boundary of the curve divided by z minus a, and then integration will give the value of the function, right? It means that it focuses on finding the value of an analytic function at the point z equal to a, which lies inside the curve C, right? And that value is actually equal to the value of the function at this point A, can be calculated, right, by using the value of the function over the boundary C, because this eventually represents that the function evaluated over the contour C, right? The function divided by z minus a. Fine. So the main aim of this formula is to find the value of the function at any point z equal to a inside a closed curve right? Rather it appears that this formula helps us to evaluate the integral, right? This is obviously true, but the main aim of this formula is that the value of the function at any point inside the curve C can be obtained in terms of its value over the contour C, right? So we have a proof for this, right? And okay, I will start with this one. Fine. Since we can see that this function, if you see this function, right, this is fz over z minus a, okay, here integral 1 over 2 pi eta c, and you know that the symbol is for closed curve since C is closed. And one more thing, here the direction or orientation of this curve is taken as anti-clockwise, right? So conventionally we take anti-clockwise direction, and that's why we have this plus sign here, right? Had it been clockwise, then this will be minus of fa. So conventionally we always take anti-clockwise direction, counter-clockwise direction, right? Or you can put a circle with an arrow here, like this one circle, and an arrow indicating the direction of this contour, right? Okay, so fz over z minus a dz, right, this is given to you, can be written as is equal to 1 over 2 pi eta c fz minus fa and plus fa, right, and divided by z minus a and then dz, right, dz. Fine. Now it will become 1 over 2 pi eta integral c, that will become fa dz over z minus a plus c fz minus fa over z minus a dz, right? And you can see that this integral is expressed as a sum of two integrals, right? And if you see this, fa is a constant, so it should be written here, right? Okay, then we will have dz over z minus a, dz over z minus a, and this fa can be written here, okay? And if you focus on this, right, say this point z equal to a, z equal to a is a singularity which lies within C, right? You can see from here. Then we can apply that result number a we derived in our last videos. The result was fa over 2 pi eta. Since this power is 1, you can see that its power is 1. Actually we have here n, and if this n is equal to 1, the answer is 2 pi eta, right? And luckily this time n is equal to 1, right? And if it is any other number, means any integer other than 1, then the answer is always 0, right? You can refer to that result in our last videos, right? And the value will be 2 pi eta, right? Okay, I'm writing here how it appeared using the result, and that result is dz over z minus a to the power n is equal to 2 pi eta if n is equal to 1 and the result is 0 if it is not equal to 1. Fine, right? Okay, and for this fz minus fa over z minus a dz, right? So I think this will become fa after cancellation, right? And we'll be left with this one, right? And but the problem is to evaluate this thing, right? Because we have already almost achieved the result. The result should be fa, and I am getting fa from here. You can see that 2 pi eta will be cancelled out. We will be getting fa from here. But for this fa, if you want to achieve this fa, this should go to 0, right? Now the problem is to evaluate this integral, right? And that integral, the value of the integral should be equal to 0 in order to achieve this FA, right? So what will I do here? You can see that this is a singularity, and the singularity lies within this contour C, and this is not having a nice shape, right? So I will replace this contour C by a small circle centered at A, right? And this is called the principle of deformation of contours, or you say it Cauchy's theorem for multiply connected region. When you replace the outer contour by simple contours or simple circles enclosing the singularity, right? Okay, you can refer to the last video to see the detailed about this Cauchy integral theorem for multiply connected domain, where we replace this C by a circle, right? I will write that first. Okay, replace contour C with a small circle centered at A, right? Mod Z minus A is equal to R, right? And R is small. Fine. I will draw that circle here. Right, and the direction should be anti-clockwise, right? And you can see that this radius is equal to R. Okay, and let me call it C small r. The name of the circle is CR, circle CR, denoted by mod Z minus A equal to R, and R is very small, right? Okay, so right, and this is my equation number 1, right? Now taking the absolute value of this integral in equation number 1 of integral in equation number 1, second integral, this one, we have mod of fz minus fa over z minus a dz, and since we have replaced this c by cr, so I will write cr here, right? And modulus, this is integration, right? Absolute value means modulus of that quantity, right? So I will be estimating it, means a value which is greater than this one, right? So that will become equal to integral CR mod of fz minus fa over mod of z minus a and mod of dz. This is by the property of integrals, right? The property of modulus on integrals, right? Okay. Now you see that this mod of z minus a is actually equal to small r. That is fine. And this fz minus fa, focus on this term, mod of fz minus fa, right? So you have to choose this small r, the radius of this inner circle, as small as possible. And when you do that, in that case, this fz minus fa will be very small, right? Why? Because A is the point, A is the center of the circle, right? And Z is a point lying on the boundary of the circle, right? So when you choose a small circle, means r is sufficiently small, in that case the value of the function at the boundary point of that circle will be almost equal to the value of the function at the center point, right? If you imagine that situation, the circle is small, right? Very small. So the boundary of the function at the circumference of the circle will be almost equal to the value of the function at the center of the circle, right? Provided you choose this radius sufficiently small, right? So choose r sufficiently small such that this difference fz minus fa, right? This difference, the value of the function at the boundary point of that circle CR and the value of the function at the center of the circle are almost equal, right? Okay, you want to choose r in such way, right? Then the difference would be almost equal to 0, or you can say that is less than epsilon. Epsilon is a very small quantity, right? Where epsilon is a small positive, right? Obviously, it will be positive because this is modulus, right? So it is a positive quantity, so it has to be positive epsilon, right? Now, plugging these values here, right? I will tell equation number 2, right? Then equation number 2 becomes modulus of C fz minus fa over z minus a dz, right? And it will become less than or equal to CR mod fz minus fa, or should I replace the value of these things, and it will become less than, right? Because you are replacing this numerator by big value, right? Epsilon, right? So this time the equality will be removed and we'll have epsilon here, right? And here we would have mod of dz, and the denominator will have mod z minus c, that is actually equal to r, right? Now since, and where is my 2 pi eta? 1 by 2 pi eta. Okay, I left it here. 1 by 2 pi eta plus 1 over 2 pi eta one over 2 pi eta. Okay, and since modulus of when you apply modulus, then modulus of eta equal to 1, right? And 1 over 2 pi, since mod of eta is equal to 1, right? So in the calculation, when you took modulus, then modulus of eta became 1, right? And here we'll have 1 by 2 pi, right? 1 upon 2 pi, right? Mod of eta, okay. And ultimately it will be equal to 1 over 2 pi, epsilon will come out, right? And this r will come out, and what is this? Integral CR mod of dz, that will represent the circumference of this small circle, and that should be equal to 2 pi r, right? Okay, and that will give me epsilon on cancellation of this 2 pi r, fine. And since epsilon is as small as possible, right, and you can choose this epsilon tending to 0, right? In that case, this integral, the value of this integral will go to 0, right? Choose epsilon tend to 0 such that, right, this value integral C fz minus fa over z minus a dz tend to 0, right? And on plugging this value in my equation number 1, I will get the required result, right? Therefore, equation 1 gives 1 over 2 pi eta integral C fz over z minus a dz equal to f of a, right? This is called Cauchy's first integral formula, right? And yes, the important thing about using this formula is that you need to correctly identify this analytic function fz, right? Means this function, the integrand, should be written in this form. Fz means an analytic function over this contour C and divided by z minus a, and a is the singularity, right? Okay, and then we'll try to derive a second formula, Cauchy's second formula, right? Second formula, this was first formula, right? First formula, okay. And the second formula is for its derivatives, right? This is for fa, means to find the value of the analytic function at point z equal to a, and this second formula is related to finding the derivative of fa, right, inside this closed contour C, right? So refer to this original picture, right? Let f be analytic within simply connected domain D, right? And C is a closed curve inside it, right? For any point A inside C, right? The formula is f to the nth derivative, right, at A is equal to 1 over 2 pi eta, and this should be n factorial, right? And inside integral we have this fz over z minus a to the power n plus 1 dz, right? This time the value of the derivative of the function, right, is can be found by using this integral, right? Or we can say that the value of the derivative at any interior point of the simply closed curve C can be found in terms of the values of the function at the boundary points, right? Okay, so we'll prove this formula by using the induction principle, or we shall prove this for n equal to 1 first, and then we'll apply the induction, mathematical induction, right? Okay, so proof for n equal to 1, you can see that this will become f dash, means first derivative at a equal to 1 over 2 pi eta and integral C fz over z minus a square, right, dz. Fine. Okay, since f dash a is actually the derivative of f at the point z equal to a, so we'll apply the limit formula here, and that is limit delta z tend to 0 f of a plus delta z minus f of a upon delta z, right? And you can see that it needs the value of fa and fa plus delta z, and that can be obtained by using this first formula. Where is that? This formula, right? You need fa, you just plug this value here, and you need fa plus delta z, and that can be found from this formula. Means the second formula uses the result of the first formula, right? Okay, so it will become 1 over 2 pi eta will be appearing outside, okay, and this delta z will also appear here, and f of a plus delta z, right? So if you put fa plus delta z, we will get integral C f of a plus fz only, fz, because in place of a we have a plus delta z, so just replace a plus delta z in place of a, not in place of z, right? Okay, so this will be fz, and the denominator will become z of a minus delta z. Now it is fine, dz, and then minus of f of a, that can be directly written using that result, fz over z minus a dz, right? And since the integral is done over the contour C, right, so we can write these integrands with the minus sign together. That will become 1 over 2 pi eta delta z, and taking only one integral and then taking LCM of these two terms, I will get z minus a fz will be cancelled, and I will get, yeah, delta z fz, right, delta z fz over z minus a minus delta z minus a, and you can see that this delta z will be cancelled, right? So I will remove this delta z, So this is my f dash a, right, the value of f dash a, and where is that? Limit delta z tends to 0, limit delta z tends to 0, limit delta z tends to 0, right? Okay, and you see that can you apply this limit here, limit delta z tend to 0? Yeah, delta z tend to 0, then it will give fz over z minus a whole square as required, right? But this is not the case. You cannot take the limits inside an integral, right? Okay, so be careful at this point. Limits cannot always be taken inside the integral sign, right? Not always. So we'll stop here, and since we target this term, we want to prove this term, right? Okay, and then what do I need? I need that this term, what I have got, should be equal to what I desire, right? And if I want so, then the difference between these two should be as small as possible, right? Means 0, right? So I will take the difference of this, what I desire, and the difference of this minus this, what I got, this minus this, right? Okay, now we wish that the difference of these two answers is almost equal to 0, right? Mod of 1 over 2 pi eta integral c fz over z minus a square dz minus this, what I have got, integral c fz over z minus a minus delta z and z minus a dz, right? And I'm calling it delta t, the difference of these two terms, right, should approach to 0 as delta z tend to 0. I want this, right, in order to prove this result, this one, for n equal to 1, right? Okay, then I will do some calculation on this, and for that I have to rub this first. Okay, now picking up that delta t is equal to, and since you can see that this is 1 over 2 pi eta, and modulus of this will be 1 over 2 pi, right? That will appear outside, 1 over 2 pi, and then taking the LCM of these two terms, and that will give me z minus a squared multiplied by this, and that will be cancelled, fz of z minus a, yes, and minus of delta fz, yeah, minus delta z fz, right, minus delta z fz, and in the denominator I will be having z minus a whole square and z minus a minus delta z, right? And we have this modulus sign here, and due to this modulus sign, this negative will become positive, right? Okay, and where's that integral sign? Integral also, put an integration here, integration c dz, okay, right? Now and this will become equal to 1 over 2 pi, this delta z will appear here, right, mod delta z, and integral c fz dz over z minus a. I think I should take the modulus over each and every term, modulus of this thing, then modulus of dz, and then modulus of z minus a square, right, and then modulus of z minus a minus delta z, and in that case this equality will be replaced by this less than or equal to, right? This is the rule of modulus when you apply this over integral, right? Okay, then what do I need? I need these values, right? Okay, so first I focus on this one, z minus a, right? And again, that z minus a is equal to r. As you can see from here, is that z minus a equal to r, right? So replace contour C by C was the original contour enclosing that singularity. A small circle centered at A, and let me denote that circle by CR. That will produce z minus a equal to small r, right? And yeah, and you see this z minus a will be replaced by this one, and yeah, also function f, analytic function f is continuous on C. You know that because f is actually analytic on C, right? Not only on C but within C, means on C and inside C, right? And f has to be continuous on C, right? It implies that f must be bounded on C, because every continuous function on a closed interval or closed curve is always bounded, right? Hence f must be bounded. And what do we mean by a bounded complex function? It means that modulus of that function is less than or equal to some constant capital M, right? Where M is greater than or equal to 0, right? So this is the meaning of a bounded function, right? Mod of that function is lesser than or equal to capital M. M is a positive, non-negative integer. Okay. And I also need this value. This is now done, and this is okay, and I need this one. Okay. Now mod of z minus a minus delta z, if you watch it closely, we can write it as greater than or equal to mod z minus a minus mod of delta z and the whole mod, right? I have used this inequality, and that is using mod z1 minus z2 is greater than or equal to mod z1 minus mod of z2, right? Okay, so this is the inequality you need to know to write this. Fine. Okay, then it will become mod, it is r minus delta z, right? Okay, now I will replace these values. This is my delta t, therefore delta t will be equal to 1 over 2 pi delta z, and it will become c lesser than or equal to, sorry, mod fz will be replaced by capital M, right? And mod of z minus a whole square will be replaced by, is that r square, and this will be replaced by r minus delta z, right? And then mod of dz, right? And this m is a constant, it can appear outside, right? And this integral c mod dz will be actually the circumference of that circle, small circle CR. I should write CR here, CR, okay. And it will become 1 over 2 pi and delta z, and this will be m will appear here, and this will become 2 pi r, the circumference of this, that is small circle, right? Integral of c on CR of mod dz, right? And in the denominator we are having r square into r minus delta z. Okay, so one r can be cancelled, r, but ultimately this term will go to 0. This term, whole term, will approach to 0. I will write it here. This term will approach to 0 as delta z tends to 0. So this is what we require in order to get that f dash a, this value, equal to the required value, right? See this, what was our delta t? Delta t was actually the difference between what we desired and what we got, right? And this is approaching to 0, so hence the result. Hence the result is proved, right? And similarly, using the same argument again and again, we can prove that f of double dash a is equal to, right, 2 factorial over 2 pi eta integral of fz over z minus a whole cube dz, and so on, right? So on using induction we can prove that result, right? Using induction on n, we get the result, right? We get the result, that result, nth derivative result, right? So these are the two Cauchy integrals formula, and again I am repeating that this formula tells us that the value of the function, analytic function, at the point which is inside a closed curve C is actually given by the value of the function at the boundary points, and this indicates the rigidity behavior of an analytic function, right? They are said to be rigid functions because the value at the center point or the inside point can be governed by the value at the circumference or value at the boundary points of contour, right? That's why we are calling them rigid behavior function, analytic functions, right? So we'll take examples of these two formulae one by one. Taking first example, example number 1. Okay, evaluate integral closed along closed curve C e to the power z over z, okay, dz, where C is the unit circle centered at origin, right? And direction is not given here, so conventionally you take anti-clockwise direction, right? Okay. Solution. So what do you need? You need to draw this circle. The circle is mod z equal to 1, right? This is the circle, and the direction is taken as anti-clockwise. This is C, x-axis, and this is y-axis. Okay, and you just focus on this. If you focus on this term and the numerator also, the numerator is e to the power z, right? And it is analytic inside this circle. E to the power z is an entire function, right? And if you focus on this denominator, and this denominator is z, and if you put this denominator z equal to 0 in order to find the singularity, right, you can easily see that z equal to 0 you will obtain from here is the singularity, and that is lying inside your circle, this point, right? Z equal to 0, right? So you need to write this integral in the form of integral fz over z minus a, right? So fz should be analytic function inside that contour C. So luckily this time no modification is required actually. So this is my fz, right? Here fz equal to e to the power z. If you compare this integral with the Cauchy's first formula, right? And we will have formula then integral of this thing e to the power z over z dz. So that will give you 2 pi eta, right? And f, what is your f? Is this one, f at 0, right? And why f of 0? Because this is actually z minus 0. 0 is the singular point, right? Okay, so f of 0, and if you put f of 0 you will get 2 pi eta e to the power 0, and that will ultimately give you 2 pi eta. So this is the answer, right? Example number 2, evaluate integral z square plus 1 over z into z minus 2 dz, right? And I'm writing the contour here, mod z equal to 1, right? Solution. Here fz is actually equal to, if you focus on this contour is the same, mod z equal to 1, right? And if you focus this denominator, this is giving z equal to 0, which lies inside this circle, but z equal to 2 lies outside the circle, right? Means that it implies that this z minus 2 should be taken on the numerator, right, in order to get the fz correctly, right? So your fz would be equal to z square plus 1 over z minus 2, right? So this is an important step to note, that actually z equal to 0 is giving the singularity, not this z minus 2. So you should not leave this z minus 2 in the denominator, right? Rather take it in the numerator. That's what I have done. I have taken this z minus 2 here in the numerator with this z square plus 1, and that is my fz, right? So this is an important step here. Then integral mod z equal to 1 z square plus 1 over z minus 2 over z dz, means you have to write this integral in this form, right? And you can see that this will give you 2 pi eta into f of 0, and now you can put 0 here. That will give you minus 1 by 2, and 2 pi eta minus 1 by 2, and then minus pi eta is answer, right? Example number 3. Evaluate integral c. Now I will take 2 poles, right? Z minus 1 and z, fine. And here we have e to the power z plus 1 dz, and c is mod z equal to 2, right? Solution. First we will draw the picture. Mod z equal to 2, this is a circle centered at origin and having radius equal to 2, right? And if you focus on the denominator this time, and that is giving z equal to 0, that lies inside our circle, and the another one is z equal to 1, that is also lying inside the circle, right? Means this time we are having 2 singularities inside our contour C, right? C. So this point is z equal to 1, z equal to 0, and this is z equal to 1, right? X-axis and y-axis, and both are lying inside the contour C, right? So this time we cannot apply our Cauchy's first formula directly. Rather, we have to use that previous Cauchy's theorem for multi-connected region, or we call it replacement deformation theorem, right? Means where we replace the outer curve by simple curves, simple circles, right? And in that case, I have to draw 2 circles. One circle at z equal to 0, a small circle, right? And another circle at z equal to 1, both oriented anti-clockwise. This is C1 and this is C2, and this is due to the deformation theorem, where we replace the outer curve by the inner simpler curves surrounding the singularities, right? Okay, so I will write using deformation principle, or you call it Cauchy's theorem for multiply connected domain, right? Replace C by small circles C1 and C2, right, as shown in figure. Okay. Then I will write it as integral C e to the power z plus 1 over z minus 1 z dz equal to C1, the first circle, right? E to the power z plus 1, and you, if you focus on the first circle, see that circle. The first circle is enclosing the singularity z equal to 0 only, right? Okay. then if z equal to 0 is the singular point inside C1, then no need to write this z minus 1 in the denominator. You should take this z minus 1 factor in the numerator part, right? And that is the key point here. You write it like this, z minus 1 over z, right? You see that z minus 0, this 0 is a singularity lying within C1, yes, you can see from picture, right? So take that z minus 1 factor in the numerator, right, in order to get a fz, which is analytic. You can see that this function fz is analytic within C1, right? No singularity of this function lies within C1, right? And secondly, you can write the C2, right? And this time you will leave this z minus 1 in the denominator, because as you see from figure, 1 is a singularity lying inside C2, right? And this will become e to the power z plus 1 over z, right, dz. And this expression or this relation is due to this deformation principle. We replace this contour C by simpler circles, right? But while writing those integrands, right, around C1 and C2, just keep in mind the fact that the denominator should be giving the only singularity which lies inside C1, right? Okay. Then I will apply here and here this Cauchy's first formula. That is pretty simple now. 2 pi eta multiplied by this fz. This is my fz, so I will write the whole value of this fz here, and z equal to 0, because z equal to 0 is the singularity, right? And this will be 2 pi eta, the numerator function fz, and evaluated at z equal to 1, right? And it will produce minus of 4 pi eta, and it will give you 2 pi eta e plus 1, right? And then ultimately it will give you 2 pi eta e minus 2 pi eta, then 2 pi eta e minus 1. This is the answer, right? Next example, example number 4, right? Evaluate. This time I will be taking an example which uses the Cauchy's second formula, right? Okay. Evaluate. See, let me take here z cube e to the power minus z sine z dz, and this c is actually mod z equal to 1. Okay. Solution. If you draw this circle, this is again mod z equal to 1, this circle, right? Okay. And if you focus on the denominator part, this is z cube, right? Okay. So 0, that will give 0, and which lies inside this circle, right? So we can apply Cauchy's formula here, and obviously Cauchy's second formula, just see this power z square. This is of the form z minus a whole to the power n, right? Okay. Here fz equal to how much? E to the power minus z sine z, right? And what do we need? We need to write this integrand as c e to the power minus z sine z z cube dz, and you should compare this integrand with that Cauchy's second formula, right? And you can see that z cube means z to the power 2 plus 1, right? And the value of n is equal to 2 here, right? And I will apply the formula, and that formula is 2 pi eta over, I think that will become 2 factorial, because n is equal to 2 here, right? And d square of dz square of this fz. So this is fz e to the power minus z sine z, and then we put f, actually that is f of double dash. I should write in that notation. That was actually f of double dash a, and what is a? Z equal to 0, right? We should draw the picture here in order to understand it correctly. This was a circle C, and direction is anti-clockwise, and the circle is mod z equal to 1, right? Okay. and this is a singularity z equal to 0 here, z equal to 0, right? Okay, so this will be a formula, right? Cauchy's second formula. And what do you need? You need f of double dash 0. So what we'll do, we'll differentiate it twice and we'll put 0, right? So differentiating it twice, I will call it equation number 1. Okay, f dash z will give you e to the power minus z cos z minus e to the power minus z sin z, right? Differentiating it once. Now differentiating it again, e to the power minus z minus of sin z, then minus e to the power minus z cos z. Okay, and it will become minus e to the power minus z cos z and minus e to the power minus z sin z. And what do I need? I need f double dash 0. Therefore f double dash 0 obtained from here, that is 0, that is minus 1, and there is minus 1, that it will become minus 2, and plugging this f double dash 0 here, equation number 1, I will get the value of the integral e to the power minus z sin z over z cube dz equal to, this 2 and 2 will be cancelled. I think minus 2 will appear, minus 2 pi iota will be the answer, minus of 2 pi iota, this will be the answer, right? And this is a numerical using that Cauchy's second formula, right? Okay, example number 5, evaluate integral c z, and let me take it z plus iota, right? dz, fine. And if I take square here, square, and z cube plus 2, okay, z cube plus 2, where c is as shown in figure, right? So contour C is shown here, is like this, x-axis, and this is y-axis, and 0 and minus iota, this is 0 minus iota, right? This is C, right? And it is of not of that familiar shape as we have been taking circle or ellipse, right? It is looking like a figure of 8, right, placed horizontally. And this is also not a simple closed curve, because the curve is intersecting itself, so it cannot be called a simple closed curve. But the hypothesis of the theorem says that the curve C should be simple curve, right? But this time in this numerical, the C is not simple curve. But in spite of that fact, the formula still holds, means we can still use that formula by breaking this not simply closed curve into union of two closed simple curves like this. If we cut at this point like this one, this thing, right, then it will become two simple closed curve. One is this one and second is this one, right? Okay. Solution: writing C, curve C, as a union of two simple closed curves C1 and C2 as follows, right? If you see the picture, it will become like this, and another one will appear like this, right? X-axis and y-axis, right? And now you focus on this function this will give you z equal to 0 and this will give you z equal to minus iota, right? So z equal to 0 is here, z equal to 0, and that is enclosed by this simple curve C1, right? And the another singularity is z equal to minus iota, it is here, z equal to minus iota. I will put 0 and minus iota here in the question, minus iota, right? Z equal to minus of iota, fine. And this is your C2, right? And both are having anti-clockwise. No, this is not anti, this is clockwise. Sorry, this is clockwise, this is anti-clockwise, this is fine. This arrow is like this, anti-clockwise, right? Okay. Now, you write this whole integral as a sum of two integrals, right? Therefore, your integral z cube plus 2 over z plus iota whole square dz can be written as union of two integrals along curve C1. That will be z cube, and be careful at this point when you write C1 here, right? Means the first curve C1, and see the orientation, it is plus, fine, and it is enclosing the singularity z equal to 0, right? And it means that this z equal to 0 will remain here, and this z plus iota is whole square will appear in the numerator with this z2 plus 2, right? Okay, dz. And now the second integral along C2, you see this, right? And when you see this, see the orientation is clockwise, but we need anti-clockwise rotation according to formula. The formula has been derived for anti-clockwise orientation, right? That's why we put minus sign here, right? And this time we have z equal to minus iota as a singularity, so leave that function z plus iota whole square in the denominator, and the z can be taken here. Okay. Now the only thing which is remaining is to apply that formula correctly, right? And now focus again, this is z equal to 0, and this is not the 2 or 3 power, this is only z power, and this is iota square. So this part will be using Cauchy's first formula, and for this part Cauchy's second formula, right? So for this part 2 pi iota, and this fz, the numerator part, evaluated at z equal to 0, right? But for this thing 2 pi iota over, I think it is 1 plus 1, and n is equal to 1 here. This is 2 means 1 plus 1, n equal to 1 here. That will be 1 factorial multiplied by f of dash, first dash, evaluated at z equal to minus iota, where fz is the numerator part, z cube plus 2 over z, right? So this can be evaluated, it will become 0, 2 and 2 upon iota square, and that will be minus 2, then minus 4 pi iota, minus of 4 pi iota. And if you evaluate this, if you derivate this, this will become z square plus 2 by z, and that will become 2z minus 2 upon z square, and you put minus iota here, right? Okay, minus 2 pi iota, okay, and it will become 2z minus 2 upon z square, it's a differentiation, and then we'll put z equal to minus iota, right, equal to minus 4 pi iota minus 2 pi iota. Plugging minus iota here will produce minus 2 iota, right? Minus 2 iota, and here it will produce iota square minus 1, that will become plus 2. I think this will be added up, yeah, minus 4 pi iota and minus 8 pi iota, and it will become plus, and then iota square minus, okay, 4 pi. So this is the answer, right? So this is the value of the integral, and you can see that the formula still holds for curve C, any curve C, closed curve C, which is not simply closed because the curve is intersecting itself at this point, right? Okay, taking another example, maybe the last one, in which identifying the numerator function fz is not easy. Example number 6, evaluate capital I equal to iota upon 4 minus pi integral and dz over z cos z, and let me take it mod z equal to 3. Yeah. So mod z equal to 3 is the circle, and you see that dz over z cos z, and you see this cos z is present here, transcendental function, right? So first we'll draw that mod z equal to 3, and then we'll find the singularities of this function, right? The solution, if you draw the figure, that is very simple. Z equal to 3, mod z equal to 3, circle centered at origin, and the radius is equal to 3. So the orientation is taken anti-clockwise, right? And you can see that if you put this a denominator equal to 0, that will produce z equal to 0, and cos z is equal to 0 at z equal to plus minus pi by 2 and plus minus 3 pi by 2 and plus minus 5 pi by 2 and so on, means odd multiples of pi by 2. Okay, but only two of them, means pi by 2 and minus pi by 2, will lie inside this circle, because pi is actually 3.14 and 3.14 divided by 2 will be almost 1.5 something, right? Okay. And what about if I take singularities are given by putting z cos z equal to 0, and that will give you z equal to 0 or cos z equal to 0, right? And that will produce z equal to 0, and from here we'll get z equal to pi by 2 plus minus pi by 2 plus minus 3 pi by 2 and so on, right? Now we investigate that how many of these singularities lie within this contour C. This is obviously lying inside C. This is z equal to 0. Plus minus pi by 2 will lie inside it, because 3.14 by 2, right? 1.5 something. And yeah, only these two, plus minus pi by 2, will lie inside this. I think pi by 2 will be here, not here, pi by 2, and here we'll have minus pi by 2, and all of these singularities will lie outside the contour C, right? So our main interest is to focus on these three singularities, right? And since the outer curve is enclosing three singularities, we have to again use that deformation principle as is used in our last numerical, where we replaced this outer curve C by a small circles C1, C2 and C3. See, three circles. First circle is this one, C1, and then C2 and then C3, and all of them having orientation anti-clockwise, C1, C2, C3, right? So using deformation principle, replace C by circles C1, C2 and C3 as shown in figure, right? Okay. So writing this original integral I equal to iota over 4 minus pi. I think we should leave this factor, and should I write it as I1, right? And I1 is this thing, right? I over 4 minus pi, and let me say I1, say, right? And I'm writing here I1, fine. So I1 is equal to integral dz C1, and since you see that C1 is enclosing singularity minus pi by 2, right? And this is an important danger point. If you see that this function, I will write the function first, z cos z. Okay, now C. Okay, so if you write here C1 and then you write here C2 and then you write C3, right? First you focus on C2. The C2 is enclosing the singularity z equal to 0, right? And you see that z equal to 0 is given by this function, not by this function. Z equal to 0 was given by z only, right? Fine. So I will leave this z in the denominator and take this function in the numerator. That will become 1 over cos z, or you can write it as sec z dz. That is fine, right? But what if I see this C1, right? And you see this C1. C1 is enclosing singularity minus pi by 2, right? And minus pi by 2 was given by cos, as well as plus pi by 2, which is lying inside C3, was given by cos. Now, so what should we write here? Dz, obviously this z should be taken in the numerator part like this. And what about this cos z, right? Should we write this cos z here like this? No. Why? You can see that C1 is enclosing minus pi by 2, right? So the only thing you want in denominator is that the denominator should be written precisely in the form of that formula. The denominator of the formula is this integrand, means z minus a whole to the power n plus 1. The term here should be exactly similar to z minus a, means some factor, z minus a means z minus singularity whole to the power n plus 1, right? But this is a transcendental function. Writing cos z here will be a complete disaster, right? So you should write here z minus that singularity. And what is that singularity inside C1? See, the singularity is pi by 2, so z plus pi by 2. The only factor that should be written here, that is z plus pi by 2, nothing else, right? But what about this cos z? Where is that? No. So we have to assume that cos z is actually equal to z plus pi by 2 multiplied by some arbitrary function gz, right? And that arbitrary function, which is non-zero at minus pi by 2, should be written here like this: 1 by z gz, right? I will write here what is my gz, right? Similarly, you can see that for this C3 part, I have to write dz here also, dz plus, and this is my 1 by z, 1 over z, right? Similarly, you see this C3. C3 is enclosing singularity z equal to pi by 2, right? So if C3 is enclosing singularity z equal to pi by 2, so in the denominator we should only have z minus pi by 2, right? In order to use that Cauchy's formula. And obviously this 1 by z should be taken here, and the remaining function, again this time I am assuming that cos z is actually equal to z minus pi by 2 multiplied by some unknown function, let that be hz or gz again, okay? And in that case I will write that function here, right, with this z. hz dz, right? Clear? Where we have assumed that cos z is actually equal to z plus pi by 2 into gz, right? And g at minus pi by 2 is not equal to 0, right? Because you are assuming that cos z is actually equal to z plus pi by 2 multiplied by some function, and that function should not be equal to 0 at this point, minus pi by 2, because z equal to minus pi by 2 is a singularity of order 1. You can say that order 1, because we are obtaining z equal to minus pi by 2 from here, right? So this is a key point. And similarly for this thing, we will write that later. And what do I need? If I need to, okay, and I will write that also. And cos z, and this is for where this for or inside C1, and cos z for C3, cos z equal to z minus pi by 2 h z, where h of pi by 2 is not equal to 0 inside C3, right? And now I will apply formula on these 1, 2 and 3 integrals, right? And this information will be used later, right? Okay, now apply the formula here. Then I1 equal to this will become 2 pi eta multiplied by the numerator, that is 1 over z gz, evaluated at the singularity, and that is z equal to minus pi by 2 This is just the Cauchy's first formula, right? Now see this 2 pi eta, and the numerator means the function fz evaluated at z equal to 0, and the third one 2 pi eta 1 over z h z evaluated at z equal to how much? Pi by 2, right? And you can plug this z equal to minus pi by 2 here, right? And this will be g of minus pi by 2. I am doing the same step here. Z equal to minus pi by 2 here, that will produce minus 2 by pi, and inside g I will be having g at minus pi by 2. And similarly for this one, sec 0 is equal to 1, that will produce 1. And similarly for this one, that will be 2 by pi h evaluated at pi by 2, right? And now I need this g of minus pi by 2 and h of pi by 2, and these values will be given by these two results, right? Now cos z is equal to z plus pi by 2 multiplied by gz, right? Now you differentiate this, differentiate. On differentiation you will get minus of sin z equal to z plus pi by 2 g dash z plus zz, right? And what do we need? We need the value of g at minus pi by 2. So I will plug z equal to minus pi by 2 here, put z equal to minus pi by 2, and that will give me sine of minus pi by 2, that will be 1, this will be 0, and this will be g at minus pi by 2. This is my value of g minus pi by 2. Similarly, picking up the second relation, cos z is equal to z minus pi by 2 h z, and on differentiating it will produce minus sin z equal to z minus pi by 2 h dash z plus hz. And since I need the value of h pi by 2, I will plug pi by 2 here, put z equal to pi by 2, and that will produce minus 1 sin 90, right? Equal to, that will become 0, and h at pi by 2, right? So I have got the values of these two unknown constants, and will plug those values here in my I1. Therefore I1 will be equal to minus 4 pi eta over pi, and this value is g minus pi by 2 is 1, fine, 1, and then plus 2 pi eta, and then plus 4 pi eta over 1 by pi, and the value is minus 1. Ultimately that will become pi will be cancelled, this will be minus 4 eta, and this will be minus 4 eta, and those will add, that will give you 2 pi eta minus 8 eta, right? And I think we can take common, eta can be taken common, as well as 2 can be taken common, right? 2 eta, and inside bracket will have pi minus 4, right? And this is my I1. The question was to evaluate I, and that is actually equal to I over 4 minus pi multiplied by the value of I1, and this I1 is this one, 2i pi minus 4. I think this pi minus 4 will be cancelled, eta square will be minus 1, right? And that will be minus 1 and minus, okay, that will be 2, right? Okay, so this is the answer, right? And we have seen in this numerical that it is very important to pick up the correct fz, an analytic function which is analytic over this contour C. You see that this time the numerator was containing an trigonometric function or transcendental function, right? And at that point, picking up the correct fz is very important, right? As compared to these numericals, where picking up the fz is very easy. You just take that factor which is non-zero at this singularity, you take that factor in the numerator and you just apply the formula, right? So this is it for this video, Cauchy integral formula. And again, this formula, the both two formulas are not about finding the value of the integral, rather they are about the finding the value of the analytic function at the point lying inside the closed contour C, right? And we'll take something more on complex integrals in our next video. For this video, thanks.